Hi. So we will start chapter 12, and chapter 12 is kind of a funny beginning. Like we start off with talking about slopes and lines and graphs, like we were in algebra. And I told you like we had minimal algebra in this class, and I could count on one hand, like when, less than how many fingers I have on one hand, of how many times we use algebra in this class. So the first section in chapter 12 is just algebra. And then the rest is like grabbing what we know from the lines of algebra to like integrate with our statistics. And I really do like this chapter a lot because not only do we find relationships between two variables, but also how significant the results can be. Like, so some things can be related, they have high correlations. I think that there's a website with a bunch of funny correlations, like how much butter a couple, each person in a relationship consumes and a divorce rate. So if we eat less butter, most likely we'll have less divorces, right? No, so butter doesn't cause divorces, right? So there's a difference between causation and a relationship. So there's like a lot of these funny relationships between, I think it was like how many stars in the sky and how many car accidents. So if we could get rid of some stars, like would we have less car accidents? And no, there's no causation. Stars don't cause accidents, right? So, but there is a relationship. So even though these are funny things that are related to each other by the process of like statistics and mathematics, is it really significant, right? Is it really significant about how much butter I'm eating and whether or not I'll get divorced one day, right? And no, really, the significance is low. So we're going to find that there are relationships between two variables, but the significance of that relationship we're also going to test. So, okay, so let's just start with algebra on the lines. Let's just get it over with, right? We have to just rip the band-aid off, okay? So here, um, with linear equations that we can remember, right? Linear equations in two variables have two variables, coefficients in front of each variable, and equal to some number. So it has like an equal sign, it has a y and an x. The power on x and y are 1, right? And we call this form here the standard form. And of course, you can remember slope intercept form, right? Which we're going to discuss too. Okay, so some of these lines do a few things, right? So let me go ahead and draw a few grids here for us. One, oh, let's do undo. Let's do another one. And one more. I think those are good. Okay, so the first one we say we can do is falling, right? So left to right. So this graph will fall left to right. And when it falls, this means the slope of the graph is negative, right? And then we're going to go ahead and draw more lines here. And as the slope increases, the graph gets steeper. So like kind of like that. Okay, so we can say as m increases, the slope is steeper. And I mean like absolute value of slope. So even though the slope here will be negative, if it's absolute value 4, it's going to be steeper than one that was 1/4. Okay, and so here in the next one, so that's like 1i, The second case is you can guess to be when the graph is rising left to right. So we see the graph is rising left to right. And this would mean that the slope is positive. And the same thing as m increases, right? So we could say as absolute value m increases, the line is steeper. The line gets steeper. Yeah. Okay, so those are the two, right? Like they fall or they rise. So the last one is when they are just like either constant or vertical, right? So let's go ahead and draw those two lines. We'll do vertical, okay? And then let's do green with the constant. So this graph here is like a y equals k, right? It's a constant function. It's like y equal 5 or 4. And here the slope is equal to 0 because there's no rise or run. It's not changing. With vertical lines, it's a little bit different conversation because vertical lines are not functions. And so they don't function the same way as 1i, 2i, or in this case, this would be 3i. So because it's a vertical line and the actual x coordinates are not changing, so this is something like x equal h, and all y values are changing. So there is some change to the rise, but there's no like movement horizontally. So unfortunately, we don't do much with these lines except we say that they have an undefined slope. So those are like the four cases that we have with lines. They're either going to fall left to right, rise left to right, stay constant left to right, or go rise bottom up, right? Bottoms up. And that would be undefined slope. Okay, so that would lead us into the idea intercept form of a graph. So let's go ahead and talk about the slope in terms of mathematically, right, numerically, instead of just like looking at a line. So the slope of a line does measure the steepness, right? M, we denote M because some mathematicians said it was modular slope. As the absolute value of M increases, the line becomes steeper. We already talked about that. And then as the line rises left to right, has positive slope, falls, has negative. And then the actual quotient would be the change in the y over change in the x. So, which we displayed up here. Let me go ahead and we just put together all of these, and then the only difference is that we have that horizontal vertical line there. Okay, so then the slope-intercept form will give us the y equals mx plus b. Okay. And that's y equals mx plus b. So remember in standard form it was ax plus bx equals c. We rewrote it to have the y on the left side, mx plus b, where m is the slope and b is the y-intercept. So when we call b the y-intercept, essentially it's just a starting point. So we kind of just start here on the y-axis and then apply the slope. So let's go ahead and graph using this technique. So 1i is to identify the y-intercept. So the y-intercept is this, remember the b, right? This is like y equals mx plus b. So here, the y-intercept is 0, 1. And then that's where we're going to start. The second part is we'll go ahead and start at the y-intercept and then apply the slope. So then in the third step, let's go ahead and identify the slope. So the slope is equal to, in this case, I can see it is a -2. So let me note some things there. Because the slope is negative, we know that this graph or this line is going to fall left to right. Okay, and then because m is equal to -2, that is like -2 over 1, which is like our rise over run. But we know that when the slope is negative, we just rise down, right? But it's just like this common language that we use of slope is rise over run. Okay, and then we want to make sure that the last thing we want to do is just to make sure we get a good line. So I think the best thing to do is to make sure to have 2 additional points other than the y-intercept. Okay, so let me get my blue graph out, my blue little marker. Okay, so I'm going to start at 0, 1. So here's 0, 1. And I'm going to apply the slope, which is rising down, right? The negative says we're going down 2 units, but always moving to the right 1. So let me go down 2 units to the right 1. Down, and then from this point go down 2 units and to the right 1. And we have 2 additional points, like in number 4, we have 2 additional points other than the y-intercept. But I mean, you could do it, more if you wanted. And you could work your way backwards too, because there's some over here, right? If I went down 2 to the right 1, I'm going to do the opposite and go up 2 to the left 1, up 2 to the left 1. So you can always just follow the pattern. That's why I like love lines so much, because it's just so easy to graph them. Okay. And so let me just note how we did that. So let me note here. So we started at the y-intercept, and then you went down 2 and then over 1. Right? So it's just a pattern, right? It's just we keep doing that over and over. Okay, let's go back. Let's keep going with more review on lines. So then we talk about the rate of change. So because the slope is constant, that means that we could say that, well, it's the average rate of change for every x value that we have. So if we are at 1, 0 or 0, 1, I'm going to move down -2 over 1. Is that going to change from that point to the next? No, I'm not going to go up 5 and then over 100. I'm still going to go down 2 over 1, down 2 over 1, down 2 over 1. And so therefore, it's just an average rate of change. It's just changing at a constant rate. And so therefore, we call the slope an average rate of change. And really, that is the real name for slope. We just call slope as we introduce like graphing and lines. But in reality, there are a lot of applications that use linear models because it's a constant rate of change. So this is one example, like a cost when you rent a car. The function c of x, where x is the number of miles driven, it's $48 a day no matter what, and then $1.55 per mile. So When you rent a car, they tell you it's $48. You can sit in the car in the parking lot and never drive it off, and you're going to still pay $48. So you have a flat fee of 48. That's fixed. It will never change. And in fact, you don't start that amount doesn't increase until when? Until you start the car and actually start driving it for miles, and then you get charged this $1.55. So you pay $48 no matter what. You can sit in the car all you want, but the moment you turn it on and you start driving places and miles go by, every mile will cost you $1.55. So the cost is changing depending on how many miles you drive, right? And no matter what, though, you're going to pay that 48 bucks whether you drive it or not. So in this case, we call the independent variable independent variable. Oops. Um, the input, right? And it's really just like the value you put in to get something, right? So value putting in. And really what we're doing is seeing that, well, they can't give me a total of how much I owe the company for renting the car unless they knew how many miles I drove. So because the cost is dependent upon how many miles I drive, then miles doesn't depend on anything. It's just I'm free driving and then I just pay later. It doesn't depend on anything. So the independent variable in this case would be X. And what is X? X is the number of miles. So the dependent variable is the output. It's what I'm getting out. And we call it dependent because it's the variable that depends on the independent variable to get an answer. So if I went to the register at the car place, I would say, how much do I owe? They're going to immediately ask, well, how many miles did you drive? So because the cost is dependent on the number of miles, cost is the dependent variable. So the dependent variable is C, which is the cost, right? And the units are in dollars, right? Because we're in America. So let's keep going. So now we're going to get into like the line part where the slope of the linear function is the rate of change, right? So the slope now is the rate of change. So what is that? Well, remember that what is changing, right? It's if I have the number of miles, then that I'm getting charged $1.55 for every mile, and that's going to change the cost for every mile that passes by. So the slope is going to be that rate of change, that rate I'm paying per mile. So the rate I was paying per mile was $1.55, right? But what are the units? Well, it's not a dollar 55. It's not $1.55. That's only $1.55 for 1 mile. But what if I drove 5? Right? Then you would say, well, just take 5 and multiply by a dollar. So see how like now it's like the units aren't just a dollar, right? So the units have to be dollars per mile. And what essentially it is taking the independent variable units and the dependent variable units and putting the dependent variable units on top per and then miles, which is the dependent. So it's just using A and B units and putting them like, here's this per and then this one. And the y-intercept is that fixed amount, right? It's like if I didn't drive the car off the lot, I'm paying $48, right? So no matter what, the y-intercept is 48, and the units on that is not a change. That never changes. That is fixed. So it's just dollars. And if I put this all together into a linear function, cx equals mx plus b, then I would say c of x is equal to $1.55, right? X plus my y-intercept of 48.